Okay, so going to try to make a video, but my computer is not really handling Camtasia and writing at the same time. So let me remind you of a few definitions. So we have some function. F is going to be assumed to be a bounded function, even if I don't say it. I'll try to say it, but assume basically for this whole lecture, not meaning not just video, not just this video, but the ones after it, that f is a bounded function. So let me remind you of some definitions. We have. I'm not going to tell you what a partition is. But the lower, if I have a partition, if P is a partition, then we define the lower Riemann sum. We're going to sum over all of the elements of the partition, and we're going to look at the minimum of f. I want to do a parentheses there. The minimum of f over the interval, or let me use x's instead of t's. Xk minus 1 to xk. I think the book uses t's. I forget. And then we multiply it by xk minus xk minus 1. And here m means the infimum of f over this set here. And then the upper sum. The upper sum is going to be basically this exact definition, but instead of minimum, we're going to put maximum. Or instead of infimum, we're going to put supremum. So supremum of f over the set. Yes, my tablet here is having a little problem keeping up. And we defined the lower Darboux integral of f to be the supremum of the lower sums. So we look at the set of partitions of the interval a to b, and we form the lower Darboux sum for each partition, and then the lower Darboux integral is going to be the supremum, and the upper Darboux integral is going to be the infimum of the upper sums. And if the lower Darboux integral is equal to the upper Darboux integral, then we say f is integrable, and the integral of f from a to b is equal to whatever this common value is, L of f, U of f. Okay, now a question that we want to ask is, okay, so if I can find a partition that gets me really close to the lower, so let's assume that L of f is equal to U of f. If I can find a partition that gets me really close to L of f, is that partition also going to get me really close to U of f? In other words, if I can find a partition such that L of fp approximates L of f, will that partition satisfy the property that U of fp also approximates U of f well? And also the other way around. I want to ask this question the other way around. If I can find a partition that both approximates L of f well and U of f well, does this mean that L of f and U of f are close to each other? In other words, if I can find a partition such that L of fp is close to L of f and U of fp is close to U of f, does this mean that L of f is close to U of f, or in particular L of f equals U of f? Okay, and so that is what the content of this theorem says. So the first theorem that we're going to look at today says a bounded function, a bounded function f on an interval a to b is integrable. I'm going to abbreviate this as intable. If and only if, for all epsilon greater than 0, there exists a partition P such that U of f minus L of fp is less than epsilon. Okay, I'm going to prove this obviously on the next slide, or I'm going to prove it obviously. The non-obvious thing is that I'm going to prove it on the next slide. But let me talk about this for a second. So notice another way to rewrite this inequality is to say that U of fp is less than L of fp plus epsilon. Now, if I want to prove that two numbers are equal to each other, I need to prove one is less than or equal to the other, and the other is less than or equal to the one. But notice we already know, from what we saw on Monday, we already know that L of fp is always less than or equal to U of fp. And if the inequality we have up here is true, this says U of fp is less than L of fp plus epsilon. And so if epsilon goes to 0, what this tells us is that L of fp is less than or equal to U of fp, and that's less than or equal to L of fp. In other words, these are equal. And so that is going to help us prove that L of f is actually equal to U of f. Okay, so let me prove this on the next page. So we want to prove, so I'm going to first prove that if that inequality holds, then the function is integrable. In other words, what I need to show is U of f is less than or equal to L of f. Since, like I said in the previous slide, we already know that L of f is less than or equal to U of f. That was a theorem that we proved on Monday. And so what we really need to show is that U of f, this is what we need to show. U of f is less than or equal to U of f, but we're going to give ourselves an epsilon of room and show U of f is less than L of f plus epsilon. Okay, so how are we going to do this? Well, we know let P be a partition. Let P be the partition with L of f, or U of f, P minus L of fp is less than epsilon. Then we know that U of f, so U of f is the infimum of all of the U of fp's. So I know that U of f has to be less than or equal to U of fp. This inequality here tells me U of fp is less than L of fp plus epsilon. If I just add L of fp to both sides, I get U of fp is less than L of fp plus epsilon. Now L of fp, so L of f is defined as the supremum of all of the L of fp's. So this means L of fp has to be less than or equal to L of f, and then carry on the epsilon. So in other words, what this shows is U of f is less than or equal to L of f plus epsilon. In other words, since we already know that L of f is less than or equal to U of f, this shows us that U of f is less than or equal to L of f. In other words, this tells us U of f is equal to L of f, which is exactly what it means for a function to be integrable. Okay, so now I want to prove it the other way. Now I want to assume f is integrable. Assume f is integrable. Okay, so if we assume f is integrable, what can happen? I want to show that U of f, I want to show that U of f, I want to show that there is a partition where U of fp minus L of fp is less than epsilon. This is the thing that I now want to show. WTS means want to show. This is what I'm trying to show now. I want to find a partition that satisfies this. Well, what I know, if f is integrable, then u of f is equal to L of f. Okay, and so now what I'm going to do is I'm going to find a partition that gets me within epsilon of u of f, and I'm going to find a partition that gets within epsilon of L of f. So those are going to be two different partitions. So let P1 is going to be a partition that approximates u of f well. In particular, u of f is going to be greater than u of fp minus epsilon over 2. I'm going to add these together, so I need it to be epsilon over 2. See, I know that u of f is always less than or equal to u of fp. But if I subtract off an epsilon over 2, again, this is just that principle that if I have a set, I can always find an element of the set that's within epsilon of the infimum. So P1 is going to satisfy this, and then P2 will satisfy L of f is less than L of f P2 plus epsilon over 2. Okay, so again, I know that I can find a P1 and P2 that does this. Let's just look at the P1 argument again. What I'm doing is I'm finding a partition P1 that gets me within epsilon of u of f. And since u of f, or epsilon over 2 of u of f, and since u of f is defined to be the infimum of the u of f p's, I know I can do that. This is the principle that we've seen in the class from the very beginning. And similarly with P2. And now, let me just write this over here. P is going to equal P1 union P2. Okay, so what do I know? I know u of fp. So there's this general principle that whenever, so we say P is a refinement of P1 and P2, meaning P1 and P2 are both included in P. And there's this intuition that says whenever I take a refinement of a partition, the upper sum is going to go down and the lower sum is going to go up. So I know that u of fp is going to be less than or equal to u of fp1. And this inequality here says u of fp1 is less than u of f plus epsilon over 2. And I know that u of f is equal to L of f. That's because f is integrable, so this is L of f plus epsilon over 2. If I look at this inequality here, this says L of f is less than L of fp2. I'm going to run out of room. Is less than L of fp2 plus epsilon over 2, and I have another epsilon. So this is going to be plus epsilon. There's an epsilon over 2. I'm adding it to that epsilon over 2. That gives me 1 epsilon. Okay, and now I know L of fp2 is going to be less than or equal to L of fp, and then carry over the epsilon. And again, this inequality happens. This was a theorem that we proved on Monday, but the intuition is that whenever I refine a partition, the lower sum goes up, the upper sum comes down. So P is a refinement of P2, so L of fp2 is less than or equal to L of fp. Okay, and so P is going to be the partition. This P is equal to the P union of P1 and P2. That's the partition that we have found here. Overall, this inequality says u of fp is, there's a less than, so everything is going to be less than. U of fp is less than L of fp plus epsilon. Okay, so that was it for this video. We will prove some other theorems and look at some other definitions in upcoming videos.